Bismillahirrahmanirrahim. Last lecture में basically I was trying to cover the material in lecture 7 over here, which is on histograms. So before I continue with that, I would like to first of all say, okay, last lecture is available taped, and also this lecture 7, is available in the videotaped form, and there is a PowerPoint that we were looking at last time. That's not what I wanted to do. इसको डाउनलोड कर लेते हैं. So, what I wanted to say was, before we get started on the formal material, some motivational words. And basically, the current Western theories about what knowledge is are very seriously wrong. And you can talk about it at a high level, where you can say that this is epistemology. Epistemology, the word means the theory of knowledge. What is to be counted as knowledge and what is to be not counted as knowledge. What happened in the West, very, very briefly, was that they rejected religion. They rejected their Catholic religion for many good reasons. But that led to a crisis. Because what they saw was that all of the human beings in their area agreed that Catholic religion is true, and yet it turned out to be false. So consensus is not a reliable guide to knowledge. Also, if you say that this is what the elders have said, and so we will follow it, that is also not a reliable guide to knowledge. Incidentally, this is what also the Quran says, that in a question answer with Ibrahim alayhi salam with his Qawm, he says that, why do you worship these idols when they are of no use? So they say that, well, this is how our fathers used to do, and this is how we will do. He said, what if your fathers were wrong? So actually, translations of the Quran in Europe gave them the courage to think in these new ways, and they said, yes, everything that everybody has said in the past may be wrong. And many of them have written this, that we are starting to do a new way of thinking in which we reject religion. But now you see, when you reject religion, then you have to search for answers to very fundamental questions. How did this planet come into existence? How did human beings come into existence? What is the goal and purpose of our life? How should we behave? how do we know that killing is wrong, for example? Things like that, many simple things, which all of these, the answers are given by all of the religious traditions, but if you reject everything, then you say that then you have to think of the answers from zero. So the fundamental principle adopted by the West was something which you can call rationalism or rationality, and the basic and most important and core idea which is at the basis of Western thinking is that human reason is capable of solving all problems that we face as human beings. We don't need any assistance from any outside source. We don't need wahi, we don't need any guidance of any sort. By logic, we can figure out the answer to all questions. This is the fundamental and guiding principle. In addition, of course, we will use empirical evidence. So the philosophy of logical positivism embodies both of these principles, that there is rationality, reason, human reason, and there is human observation, and there is nothing else. No other source of knowledge is accepted as valid. So then basically science emerged as the alternative to religion, and they said that they started worshipping science, that science will provide the answer to all of our problems. And science, they thought, they had also many misconceptions about science and what is the nature of science. So in particular, they thought that the numbers quantification is very important. If something is qualitative, then it doesn't exist. If you can't measure it, then it doesn't exist. So in psychology, people started measuring intelligence and measuring trust and measuring confidence, everything they want to measure and reduce to numbers, because they think that if you can't measure it, then it doesn't exist. So this is a big mistake actually, because a lot of important things are non-measurable, and even to try to measure them is a mistake. So this worship of numbers is at the heart of econometrics and statistics. A lot of things which don't really need to be measured are being measured, and then the idea of econometrics is to derive results from these numbers. Now actually, so the way that econometrics is currently used is massively wrong. The whole methodology is wrong, and nearly all of the results that you see published are wrong. So here I am going to try to teach you how to do things right. And the most fundamental problem that exists with current methodology is that it only looks at the numbers, it doesn't look behind the numbers. And everything is happening behind the numbers. That is, you see, basically this is let me just provide a name for this. There is the nominalist philosophy, which says basically that names are everything, appearances are everything. It acknowledges, this was started by Kant, but they were a philosopher, German philosopher, but many other people have picked it up and spread it, that okay, there is a reality behind what we can see. For example, we see that the earth revolves around the sun, but why we don't know, And then there is this hidden force of gravity which we cannot see, which is the cause of this. So the nominalists deny this reality. They say that all we have is the numbers. So now, for example, if you want to find out let's say that we want to study the process of economic growth in Pakistan. So people will go and look at various variables which they think is important. For example, you might think that education is an important variable. So now you will pick up the data sets for education, anything that you can find. So we have time series on enrollment in schools and other data like that. And then you will pick up the GDP series and you will run a regression and you will say, here is the effect of education on growth. Now, this is not a valid or legitimate method to study the effect of education on growth, because it just looks at the numbers. It doesn't look at the reality behind the numbers. So if you really want to study the effect of education, then you have to go, as one statistician put it, that you have to expend shoe leather. You have to go and walk around and talk to people and look at how the world is working. And basically all of this is very qualitative information. And this is not part of the training, but actually just like the human being consists of a body, flesh, and a soul, which cannot be seen. The soul without the body is also meaningless, but the body without the soul is also meaningless. So in the West, they have discarded the soul. They don't acknowledge the existence of the soul. And similarly, they don't really study the reality which produces the numbers, because it's qualitative. It's not, you cannot look at the numbers. So you study the process, you look at the schools, and there's lots of books. I mean, are there ghost schools? What kind of schools are producing what kind of education? What happens to the students who get educated? What kind of activities do they do? Are these activities helpful for the process of growth in Pakistan? Are they harmful? Are people getting real education? What is happening to the people who are not getting educated? All of these things you have to study in order to come up with an answer to the question. But in your econometrics course, you will never hear anything like this. So, what I am advocating here is something. Currently, the econometrics that is being used might be called nominal econometrics, because they are only concerned with the numbers and the names. And what I am proposing to do is real econometrics, which is concerned with reality. And I have a couple of papers I have written showing what the difference is and how it works. And in reality. So now in this in these lectures, I am starting from zero, and my goal is to teach those parts and aspects of numbers. Just like you see, there is body and soul. So the numbers are not that we can completely ignore them, but numbers are useful, but they only have a limited role. Just like reason is very useful, but it has a limited role. There is lots of things which are not within the scope of reason. As Iqbal has said, कि मुकाम अक्ल से आसान गुजर गया इकबाल, मुकाम इश्क में मारा गया ये फरजाना. So there are lots of things, lots of knowledge which our heart has, and that knowledge is very important in understanding the reality that we are living. So in last lecture I discussed that the very basic thing is histograms. Histograms, this is the, as I said, if you start with ABC, then this is the ABC. Histograms are just a picture of the data, nothing else. So you have data which is a collection of numbers, and you create a picture of this. This is the most basic and fundamental concept, and we studied that, okay, this is the data set for the number of people in the households, and we make a picture, it comes out like this. It shows us that the most frequent, the largest proportion is at household size 7. That is, there are 26 families which had households of size 7. So this is the modal value in this population. So if these 127 houses were chosen at random, then they would be representative of the total population. Then we can guess, we can conjecture, we can hypothesize that perhaps in the whole population, from which this 127 has been chosen as a random selection, in the whole population, the number of families with 7 members is the largest number, because this is the case for our sample. Now the question of how likely this is to be true, and many other calculations we can make. These depend on probability theory, which we have not yet introduced into this course. So, but that's where things start. Then I looked at the PP per capita data, where we had 130 countries, and then I explained the process of making a histogram. So this was the histogram for countries by income, and this histogram shows us that the largest group is in the 0 to 5,000 category. So that means that the largest group of countries are poor countries relative to the others. And another thing that you can see from this histogram is that there is some bimodality, that there is a break between 20,000 to 25,000, and then there is a large group of countries which are poor, and then there is a group of countries which we might call rich. So if you have, they have separate distributions, and so if we would like to have a better idea, then we need to make separate histograms for the rich countries and the poor countries. And so this is a histogram for the poor countries, in which the categorization was split. The bin size was made 0 to 1,000, 1,000 to 2,000, instead of 5,000 in the initial graph, because if you want to look at the poor countries, then you want to have a small bin size. So one of the things that is important to understand here, these things are very much underemphasized in econometrics, is that what is going on is in statistics, econometrics, is an interaction between the human being and the data, because the West has made objectivity into the God, that we must be objective, we cannot be subjective, that the facts matter but my opinions don't matter. But these things that's not actually true. Facts and opinions are all equally important, and opinions are also facts in the sense that my opinion is also a fact to me, although it may not be to others. So what I mean to say in terms of making graphs is that there's an interaction here, there is a picture, and then there is my understanding of the picture, and how I choose the bin size will be according to what makes this picture understandable to me. So there is an interaction going on here between the data and the human being, which is one of the goals that you have to learn in real econometrics. So the object here is to, we use the data to try to understand its properties, and we try to make pictures which reveal these properties in the best way, because what we are trying to do is to create arguments using data. We are trying to convince people of something. So we have to learn to make the pictures which explain the idea that we are trying to present in the clearest possible way. There are many different types of pictures that you can make with the same data, and so you have to learn which type of picture gives which type of information, and then this has to be subjectively adjusted according to the information that you are trying to convey. So for example, here in this picture we see a little gap at around 7,000. So we might, if we were interested in making such an argument, we might say that there are some countries which are extremely poor, and then there are some countries which are sort of less poor. So in fact, if you want to make, then this graph would be useful in making such an argument, because it shows that there is a gap at the bin size of 7,000. And then you would always, whenever you are interpreting data, it's never just the numbers. You have to go behind the numbers. This is an essential component of real econometrics. So suppose I want to strengthen this argument that there are some countries which are really poor, then we look in the real world literature to see what can support this idea. So if we go, we find that the World Bank has a list of highly indebted poor countries. So we say, okay, maybe this is this category. Then we will look for a match. We look at the countries which are falling into this category, and we see if we can match them with the highly indebted poor countries. And then we will say, okay, this graph shows this division. So we are always looking for not just the data, but we're looking for interpretation in the real world of the data. So this whole course, this is the 7th lecture in it. It's the first 9 lectures are all about descriptive statistics. They just talk about how to look at data in different ways without actually doing any probability and any statistics. And so it's highly recommended that you should go through these lectures. So in the making of histograms, one of the things to understand is that as you make the bin size larger, all of the data gets clumped into small categories. You see a smoothing effect, and you see big picture, but you don't see the details. As you make the bin size smaller, more and more details start emerging, but at some point the picture becomes too jittery, too fine. So there is a optimal bin size at which you see some pattern also, but there's not too much irregularity. So here we are seeing that this is the first picture. There is a sort of a clear picture of the data here, but here we are reducing the bin size from 1000 to 300, and now we are getting much more irregularity, much more jitter. This is the same two graphs in a side-by-side comparison. you can see much more clearly on the picture on the right hand side, assuming you can. I mean, this is also something which takes practice, learning to look at histograms and to interpret them. The pattern on the right hand side picture, which has the big bin size, 1000, is much clearer than the pattern on the left hand side, which has a small bin size. Now if we go to large income countries, so those were the picture for the poor countries. Now here is the picture for the rich countries, going from 26,000 to 40,000. We have excluded the outliers bigger than 40,000 in order to be able to get more data into a particular range. One of the problems with the outliers is that if you have, for example, if you have one country which we have, I think is around 90,000, then all of this data would get compressed into about 1/3 of this or 2/3 of this, which would make it more difficult to see the pattern. So outliers are eliminated because you can see more points within a given range. So these issues are not discussed in conventional books. Now there is another kind of a histogram, which is a dot plot, which I won't discuss. So I'm just going over the last lecture, that what do we learn from the histogram? That there was a right skewed distribution, a few extremely rich countries and large numbers of poor countries, and that there is bimodality. There are two groups of countries. So one thing that we learned is that the scale on which we make the histogram is different for different sizes. If we look at the poorest countries, then the bin size from 3,000 to 7,000, bin size of 300 is relatively good. It reveals the patterns in this group, and there are lots of countries in this group. And if we look at the middle income, going from 7,000 to 20,000, then the 300 bin size is too small, and so a bin size of 1,000 suits this group much better. And if we go much higher, from 20,000 to 70,000, then 1,000 is still too small, and bin size of 5,000 is good. And this is a picture which has variable scale, but this is not well drawn by Excel, because while we have put all three categories into the same picture, the scales are different, and the eye is deceived here, because in the first part of the graph you have 300 bin size. In the second part of the graph, the bin size is 1,000, but they are taking the same space. So what should be a much larger graph has been compressed in a factor. When it's lying besides the 300, then your eye is deceived because it's not to the same scale. So you can compensate for this if you understand what is going on. But one way to avoid this problem is to use the log scale.
सर एक क्वेश्चन है
जी,
बिन साइज की सिलेक्शन के लिए कोई सिस्टमैटिक क्राइटेरिया है या
नहीं, कोई सिस्टमैटिक क्राइटेरिया तो नहीं है. Basically, what one needs is that every bin should contain more than 1 point, and there is some rules of thumb that you should try to choose bin size so that every bin has at least 5 points. So, but this is, as I said, it's the picture which determines what bin size is good, if you look at the picture. So ultimately it's a subjective decision, and this is the serious problem, that in the Western methodology, you're always looking for some objective criteria, but most of the decisions that we need to make are subjective. So this is not part of their theory. So there can be a formula for bin size, but it will not be, and there are some formulas, but formulas are just rules of thumb. Okay, use the formula, maybe If it produces a nice picture, then it's good. If not, then adjust it by yourself. So the subjective factor is not taken properly into account. So we converted the data into logs, and then we looked at the different graphs for different bin sizes. Here's the graph of infant mortality, and again this shows a bimodal distribution. Here at around 40 you have a cut, means that countries with infant mortality less than 40 per 1,000, I think it is, are in one category, and then there are countries which have high infant mortality. These are in different categories. Again, this is what the graph suggests. Now what we would like to do is to try to find some real counterpart for this. What is it that it leads to infant mortality less than 40? Maybe it's just nutrition, for example. So you could look at different countries and see, is there a significant difference? Then for the under 40 countries, maybe it's true that malnutrition is very low, or that, and for the countries with above 40, malnutrition is very high. That could be. So it is always the case that the data, the pictures, will suggest some hypothesis about reality. And so real econometrics works like this, that by looking at the picture you get some idea, and then you have to follow it up in the real world. So this is something which is not done in conventional econometrics. You just run the regression and that's it. But the reality is that the regression is never enough to prove anything. This picture is just a picture, and it makes some suggestion about what might be the cause. Now you have to actually go and expend shoe leather, walk around in the real world and find out whether or not this picture gives accurate information. It could be a misleading picture. So it's always, econometrics is always a combination of body and soul, of the numbers and the reality. And you cannot leave one part out of it. So for example, Maria Qubtiya is doing a thesis on export promotion. So we are looking at the data on exports and on GNP, and then we are looking at countries which have had good performance with respect to one variable or the other variable. Then we look at the country itself and we say that, okay, this is the country in which Korea has had high exports. So what happened in Korea? How did they get high exports? So it's not enough to just look at the numbers. You have to go behind the numbers and find out the real causes. And in all of the theses, econometrics that I have supervised, I have made sure that the students have done the econometric analysis and also the qualitative, historical, contextual, real analysis that must be used to support the data analysis. So this is the picture for 1970, and then in this there is no bimodality. In 2010 there was a bimodality. So one hypothesis that comes to mind is that something happened, some new technology was introduced which helped the countries, and it's starting around 11, which is the minimum. Now in the 2010 picture, it goes much closer to 0. So some new technology was introduced which really helped bring down the infant mortality. It was adopted in some of the countries and they managed to lower their infant mortality. It was not adopted in others, and that led to the bimodality. So this is one potential hypothesis, but in order to confirm that, you will have to go and read the literature on infant mortality, and there is a lot of literature. Okay, so life expectancies. Again, what does this picture show us? There are lots of poor countries in the left-hand side which have very low life expectancies, and on the right-hand side we have the wealthier countries which have achieved high life expectancy. Here the distribution is bimodal in 1970, so the life expectancies show that there is a distinct difference between, there are two types of countries. The poor countries have very bad life expectancies and the rich countries have much better life expectancies. So the transition from 70 to 2010 now suggests the opposite thing, that the general health measures which increase life expectancies have somehow spread uniformly, so that this disparity, the two populations are no longer separated into two. Again, this is just a hypothesis which would require confirmation by reading up on what has happened to life expectancy in different countries. So this was the histograms. The next topic is densities. You see, this is very interesting in that जो हम लोगों को बतलाया जाता है वो ये है, यानी when we are taught econometrics, कि look at the numbers and try to understand reality on the basis of these numbers, but nobody actually ever does this. It is never the case. So the methodology that you're taught is opposite to what is actually done. So what is actually done is that first you study the situation in terms of qualitatively. You listen to the stories, the history, the context. That gives you the hypotheses. And then you use the numbers to prove that you are right. So, for example, if you have a theory about the consumption function, then the numbers are used to prove that your theory is right. If the data contradicts your theory, then instead of saying, okay, I will change my theory, which is what should be done perhaps, what you do is you reanalyze the data. You try to find some way of running the regression which will prove what you have set out to prove. So actually the real econometrics, our understanding of the world doesn't come from numbers. It comes from our experience, and it comes from qualitative, historical, contextual factors. Then you try to use the numbers to prove this. So the issue cannot be resolved at the level of the numbers. You have to go back and see what was happening in the real world at that time, and according to that, then you interpret the numbers to conform with the theory that you have developed about the world by using your own understanding. So there is no answer to this question at the level of looking at the numbers. Now this one, now histogram is one way of picturing the data, and it has several defects which are overcome by looking at the kernel density estimates. So this is a much more interesting and more accurate picture of the data So, what we are going to do is to try to explain how kernel density estimates work. Again, this is just another way of picturing the data. So far, there is nothing, no theory. So far, we are working with zero theory. We are looking just at some numbers and how to picture those numbers without introducing any idea about probability, statistics, sampling, distributions. You're just trying to make a picture of the data. Now, the histogram suffers from some defects. One of them is that, you see, you have one dot and you make a bin. Now, wherever the dot is inside the bin, it doesn't matter. It counts as a number which is inside this category. So, if you have the category 0 to 500, then if a country has income 0, it falls into this category. If the country has income 500, it also falls into the country same. And if it has 250, it also falls into the same category. So they all get the same representation in the picture. So this is a little bit, it loses information about the data. Another thing is that there is some error in the data, variability. When you measure, you never measure with perfect accuracy. So a point which is at some value might also be actually nearby, not exactly at that point. So the number that you have, so your number is 249 for income, but maybe it was 253 and it was not measured correctly, or maybe it was 240 and it was not measured correctly. So the histogram doesn't take this into account, but the kernel density estimators take one point and they spread it out over a small neighborhood, so as to take into account the fact that the point is not really measured very accurately necessarily. Alright, so this lecture, the second lecture is lecture 8 on density estimation. It shows how to make kernel density estimators. And now this lecture actually contains material which is not available easily anywhere. I looked for it because I wanted to find some. And in particular, the technique which is taught here later on in variable window sizes has not been written up and is not available in packages even. So I have provided a way to do this in. Okay, we start with a simple data set which has only 6 points in it. This makes it easier it has 7 points in it. 1, 2, 3, 4, 5, 6, 7 exactly. So now this is actually to make it easy to understand what is going on. What is the data set? This is 6 years of returns on the Egyptian stock exchange. One very important thing to understand about real econometrics is that we cannot analyze numbers without knowing what they are. So you have to know, and this exactly the same set of numbers. If it is ages, then it will have a different analysis. If it is incomes, it will have a different analysis. If it is rainfall, it will have a different analysis. And you cannot do a correct analysis by just looking at the numbers. And this which I am saying is different from what is written in the econometrics textbooks. The textbooks say that the job of the econometrician is to just analyze the numbers, and there is the field expert who will study the interpretation, and they separate these two things. And these two things cannot be separated, just like the body and the soul. So here, the original data set is 7 numbers. For 7 years, we look at the Egyptian stock market and we ask, what was the overall rate of return on the stock market? So we have one was minus 55%, one was minus 50%. So there was a huge crash in the stock market in those 2 years. One is 10%, another is 12%, then there's 37% and 42% and 53%. So the initial picture has bin size of 1, and as always, when your bin size is very small, then all of the data will get their own bin separately. And so here we have a picture of all of the 7 points, but we don't really see any pattern. It's not so easy for us. This is a human limitation. Our eye does not easily pick up patterns if you have a large cluster of points which are just spaced along the axis. It can pick up some patterns. So here we can see that the middle 2 points are near 10 and 12, and there are 2 low ones and 3 high ones. Okay, so we slowly increase the bin size. So when we go to bin size 10, then the second picture is over there, and now you see there is a little bit of a pattern. The returns near 10 are more frequent than, so we can say that, okay, normal returns are around 10 to 12%, but sometimes you have unusually high and sometimes you have unusually low returns. So this is much easier to understand from this picture than from the first picture. In the third picture, we go to bin size 50, and now this is really a much smoother graph. And if this is the picture, then the same thing that I said, that there is some normal returns. And now, of course, the normal returns here, according to this picture, varies from about 25 to 75, because this is how the bin size is set up. Bin size is 50. And so, sorry, not 20, it's actually, it would be from 25 to 75 exactly. Sorry, no, that's not correct. The graph says mislabeled actually. I think this is going from 0 to 50, that is going to be the biggest bin. And then, so anyway, the picture is the same, that there is a range of normal returns, and then there are some high returns and some low returns, which this picture shows much more clearly than others. So here we discussed already that the bin positions are fixed in advance, not determined by the data. The shape is not very smooth. So now when we go to kernel density estimators, what we do is we use density at every point. We fit a normal density. So it has a smooth shape. This is now there is an issue that arises in making histograms, and that issue is how do we choose the bin size. And as we have said, if the bin size is small, then you get a rough and jagged picture. If the bin size is big, you get a smooth picture. But if you make the bin size too big, then you lose all the information, because all of the data falls into one category. And if you make the bin size too small, again you get a very jittery picture and you don't pick the pattern. So there is somewhere in the middle. So when we fit a normal density, then the same kind of thing happens. It's the standard deviation of the normal density which acts like the bin size. Now here I have 3 normal distributions. The blue one is standard deviation 1/2. It is a sharp curve closely centered on the point. If I make the standard deviation higher, then the graph becomes more spread out at 1 in the red curve. And if I make the standard deviation equal 2, then the green curve is even more spread out. So basically we are taking this point and we are spreading it over a larger and larger area. As we make the standard deviation small, every point will be sharply isolated and will be in its own category. As we make it large, then large numbers of points will come into the same category. So it's just like changing the bin size. Small SD corresponds to small bin size, large SD corresponds to large bin size. So here is the picture with SD equals 1. This is a narrow window. Now we call, in kernel density estimation, this is called window size, not bin size. So the window size is the SD. If we have small window size, which means small SD, so basically every point is replaced by a normal density. So here we have 1, 2, 3, 4, 5, 6, 7. 7 points. 2 of them at minus 56 and minus 49. You see the normal density is very sharp, and both of these points have their own curve, and 36, 41 and 52 are again getting their own curve. You see that between 36 and 41 there is some overlap, so the graph doesn't go down to 0 and then come back up. There is a little bit of an overlap. But the interesting thing is the 10 and the 12. The 10 and the 12 points, the densities which are separate for these two, they get added together. And so now the peak is higher at 10 and 12. So here is a kernel density estimator for these 6 points, which is using SD equals 1, which is a narrow window size. So one thing that you should understand is that as you make the normal density size, as you make the window size narrower, ultimately the graph will have one normal for each point. And so it will have the number of peaks in this will be exactly equal to the number of data points. Now, in this case, here, the number of peaks is not equal to the number of data points because there is, the 10 and 12 have overlapped, so their 2 peaks have been added together and they have merged into 1 peak. So, and this is also the other part, that as we make the window size larger, ultimately we'll get only 1 normal density and there will be only 1 peak. So we move from the number of peaks being equal to the number of data points to the number of peaks being exactly equal to 1 as we increase the window size. So here are some pictures for what happens as we increase the window size. And so what we will also do is not just to draw the pictures, but to give the interpretation of these pictures. So at SD equals 1, we have already seen that this is the picture. It's very rough and jagged. You can't really interpret this very clearly, except to say that there is more probability near 10 and 12 than there is at other points. Now at SD equals 10, we start giving a smoother graph. Now you should understand that in the bottom we have the normal curves for each of these points separately. The blue and the red and the green and the purple and the orange. These are all graphed separately. Then we add up all of these curves. So the purple curve is the kernel density estimator. It adds up all of the 7 different normal curves. So what do we get? Now we have something very interesting. This graph, as SD equals 10, says that there are 3 modes. So now we can say that the economy is functioning in 3 different modes. There is a low mode in which there is a peak around 50, minus 50. And then there is a medium mode which has a peak around 10, 12. And then there is a high performance mode in which there is a peak around 45 or so. So there are this graph now, it's a smooth and continuous graph, unlike the 7 points, and it gives us the 3 modes. Now when we go to SD equals 20, then we get to a bimodal graph. And now it says that okay, there is a bad mode for the economy in which the peak is minus 20, and then there is a normal mode in which the peak is around 30. Now it has, in this graph, all of the positive points have been merged into 1 because we have increased the window size. Now when we increase to 30, then now there is no separate peak in the negative, but there is still some what you call a point of inflection. There is some suggestion that there is something, that there is a big tail, the distribution is changing a little bit around minus 30 and it's getting spread out. Unlike the normal, which goes down sharply, we have a spread. And then we go to SD equals 40, and now there is only one peak. And so this is the general picture. Now the question arises, how many peaks are real? This is actually an interesting question, which is has the very strange name in statistics called bump hunting. We hunt to find out, is this bump, you can generate bumps in your kernel density function by changing the window size. So the question is this bump real or is this just an artifact of the data? As we reduce the kernel size to 0, we will get one bump at every data point. And what the meaning of this is that at every data point there is some concentration. So the next point that comes up should be within one of these curves. And this is wrong because actually the data points, those bumps are too small. The data points don't. And if so what is being suggested by that picture is that there will be nothing between two data points. And that's wrong because we know that the data is not that accurately representative of the underlying real process. But this is because we know about the stock market. In other situations, this might not be true. Depending on the reality of the numbers, we might come to a different conclusion. But in general, in typical situations, if the frequency is reduced too low, then the histogram, which has one curve at each data point, is not a true representation of the process that is generating the data. So we start smoothing. So for example, we go to SD equals 10, 20, 30. So we have 3 bumps and then 2 bumps and then 1 point of inflection with 1 bump and then only 1 bump. Ultimately, if you increase the size large enough, then you get just one very normal looking curve. So now the question in bump hunting is, how many of these bumps are real? Is this in the 3 bump graph? Are these 3 real bumps? If these are 3 real bumps, then the real economy will generate sometimes 10% or 12% return, and sometimes it will generate a 35% return, sometimes it will generate a minus 50% return. And these are the 3 most likely operations. But it could be just that this is just a jitter due to just a small sample. It's just something that happened randomly. It does not represent. So this issue, how well does my data represent the reality? This is the crucial, central, most important issue in all of statistics at all times. We have a sample and then we have a true reality which is generating this sample. So how good is the match? This is the question we are always studying throughout in our study of probability and statistics. So in bump hunting, we are trying to find out, okay, here is a bump at 10 to 12. Is this a genuine bump? That is, it represents something which is coming out from reality, or is this just an artifact of the data? It is a fake bump. So this question arises all the time. Like if you have cricket scores and some good cricket player, I don't know, current players, balle wala kaun hai? Imran Khan jo hai, suppose that we have 11 batters and one of them scores 100 and then the second one scores 72 and the third one scores 56 and so on. So we have a range of numbers. So now we can draw a density graph and we can ask the question, is this century 100 score, is this different from the rest or is he part of the same pattern? Now you see, if we take any 10 players, they will always get different scores and there will always be someone who scores the highest. So there is a question, this highest score, is it a genuine accomplishment or is this just random variation? How can we answer that? It's not too difficult. I mean, there is a systematic way to do that. We'll say, let's assume that all these players have identical abilities. They have exactly the same probability of hitting the ball. So this will be our null hypothesis. So then we look at how much variation is produced in the scores under the null hypothesis. So we can run a simulation, and this is one of the key concepts in understanding this kind of thing. That okay, we set up a random spreadsheet, and we let every person bat, and we let every person make a hit on the ball with the same probability. So he scores one, we can give him 3 probabilities. He scores a run, or he scores 0, or he goes out. So we can give a probability that the probability of getting out on a ball is 5%, and the probability of not scoring is 50%, and the probability of scoring 1 run is the remaining 45%. Okay, so this is just to set it up. Actually, what you do when you do a simulation, you try to match the observations. When you look at the real data set and you look at the probabilities of these events in the real data, and then you set up a simulation to match those probabilities. So then we set up these simulated cricket players, and we say, okay, do your simulation, and we run the simulation, and then we look at the spread in the scores in the simulation. So if we look at the spread, we say, okay, in this simulation, one player scored 30, another scored 50, another scored 60, another scored 80, another scored 100. We say, okay, on this simulation, we had 5 players, and they scored the same range that we observe actually. So then it means that the simulated players, they were all equal. We know because we set it up like that, and then we got this range. So it means that this 100 is not a very exceptional score. It means that this score does not prove that Imran Khan is a spectacular player. Now suppose that in the same simulation, we find that these players that we have set up to match the characteristics of the match, they are getting scores like 20, 30, 40, 60. And we done it again, and we get 30s, 35, 55, 65. And we keep doing it, and we get ranges of score, deviations between 0 up to 70, 80, but we never see 100. So then we see that, okay, if all players have the same ability, and and we set it up a simulation, and we repeat it often, we get a very wide range of scores, but we never see 100. This means that this 100 cannot be generated by a player who has an equal match to the other players in the game. So that proves that. Now all of these things can be done rigorously and precisely, but the thing to do is to understand the idea behind. So
क्वेश्चन यहाँ पे कि कर्नल डेंसिटी फंक्शन को 2 वेरिएबल्स के लिए भी स्टडी किया जा सकता है साइमल्टेनियसली, और उसका इंटरेस्ट रेट और इन्फ्लेशन को अगर हम स्टडी करना चाहें तो उसका हम यूज कर सकते हैं.
Then you have to use what is called bivariate density estimation. It's much more complicated, and you can not easily draw pictures of what is happening. So for the moment, the kernel density method is only for one variable to describe the distribution of that variable. For 2 variables, there are more complicated methods of trying to picture the relationship between those variables, and we have discussed that in this in a later lecture in this same course. So here is the another illustration of the kernel density. This time what we are looking at is the incomes in the countries. Again, the same 130 countries. And again, I am showing the same phenomena. These are 4 pictures with varying window sizes. So the smallest window size is SD equals 100, and this is the picture. This is the same picture that we drew for the GNP per capita. Now you see that there is a lot of rough portions in this graph at the low window size. Small window size means jittery graph. we double the window size to SD equals 200, and it starts getting smoother. We make the window size at 500, and now a pattern seems to emerge, is much clearer. You can see that there is a group of poor countries and a group of big countries, and there are lots of bumps. And again, the theory of bump hunting will tell us whether these are genuine bumps or just random erratic blips in the data. Then at the largest window size, SD equal 1000, we have clearer picture. There is one small peak, and then there is another peak around 12,000 or so, and then the rich countries have their own density. What I was doing in this was that the World Bank has the following cutoffs. It says that low income is 1,025, lower middle income is 1,026 to 4,000, upper middle is 4,000 to 12,000, and high income is 12,000 or more. Now the densities don't support these cutoffs in the sense that the division that comes out from looking at the density does not match those black lines which are separating the World Bank cutoffs. This doesn't necessarily make a difference, because the parametric density, if this is if we look at the real world factors, we might be able to find that there is something about 1,000 which is real, that at this level 1,000, all of the countries have some factor which is in common, and then from 1,000 to 5,000 we might be able to find some other real factor which is in common. But just by looking at the histogram, these are not the numbers that we would use for cutoff. So we have to ask, how did you make this cutoff and what was the basis? Because those cutoffs are important in the sense that people say, oh, this is a low income country, this is a middle income country, and this is used in arguments a lot, that Pakistan made it from out of the ranks of the poorest countries to now it's categorized as lower middle income. But who determined this 1,000? Where did this 1,026 come from? Suppose I make it 1,200. It will then have different interpretation and meaning. So you have to understand that there is an air of authenticity and objectivity that is created by numbers, and this is used by people to deceive other people into thinking that something is an objective fact when it is actually a subjective thing. Because, as I have said, in the Western epistemology, a subjective doesn't count for anything. So what you do is you make your opinion into a objective thing by converting into a number and saying, okay, this is. So anyway, so if you look at the parametric density estimates, then that will suggest cutoffs. So, for example, if you look at this density estimate, then there is a natural bottom around 20,000, and so you can say, okay, rich countries are above 20,000 and poor countries are below 2,000 according to this graph. So the cutoffs are determined by your parametric density. This is one way. There is another way, which is to use a box plot. In a box plot, you look at the first quartile, the second quartile, and the third quartile. So the first quartile is the place where you have 25% of the countries, and that is 2,500. So you can say, okay, at 2,500, we have Up to 2,500 we have the poor countries. And then from 25 percentile to 50 percentile, we have 2,500 to 8,000. So that would be the lower middle income countries. And then 8,000 to 22,400 is the third quartile. And that is at 22,400. So now the box plot cutoffs are quite good in the sense that they match the recommendation from the parametric density. So, I mean, if you look at the first cutoff, it's near a bottom, so this is a natural point at which you would cut. The second is also corresponding to a bottom, and the third also seems like a natural place for a cutoff. So this is quite different from the World Bank cutoff, but it is much easier to justify, and so one can use these to make arguments. All right, I think I will stop here and ask you to go through the lecture on your own. And you see there are 3 steps actually. You can either, usually in every lecture I have a lecture write-up. Here, for example, there's the lecture 08 density.docx. So depending on your style and method for learning, you can do one of two things. Either you can listen to the videotape lecture and then read the lecture notes, or vice versa. Sometimes if you read and try to understand first, and then you listen to the lecture, depending on your style. So those are the first 2 steps. Either you should watch the lecture and then read the lecture notes, or vice versa. Then the third thing to do, actually, which is not listed here, is that there is a comprehension quiz on the lecture which you can take. And it's I have set it up and it's available. And I have instructions on how you can do it. It's actually right here on the first page. I haven't written separately. So it's written over here. There are quizzes associated with each lecture. One is a comprehension quiz, which tests the understanding of the lecture, and the second is a computational quiz. So the first quiz is a comprehension quiz which tests your understanding of the lecture. So you should do that. Then there is a lab, a computer lab, which is in every lecture. So computer lab just is a do-it-yourself exercise, and basically all of the calculations that are made in the lecture, you are given exercises to help you go through them. It's a hand-holding procedure where you are told, okay, make this graph and here is how you do it. Click on this cell and invoke this function and do this and that and the other, so that you can replicate the material of the lecture. So after doing the exercise, then you should have some confidence in your ability to replicate the material of the lecture, so that you have this is hands-on learning, in the sense that you don't really learn anything by listening to me lecture about it, but you learn things by doing it yourself. If you can replicate what I have done, and that is the goal of the lab, then you have understood, and you will resolve these issues about window size, etc., because when you do it yourself, you should be able to understand what is going on. And then the second quiz tests your computational skills, because the lab will teach you how to do certain computations. So the second quiz will actually takes a spreadsheet and asks you to do some calculations and then report the results and check. And the quiz is built in to the QuizStar system, which is over here. So you log in and you enter your name and you go to the quiz and you take the quiz, and you will be able to see if you have understood or not. So that's all for today, Next lecture will be next week on Thursday. It's a weekly process. And these are our ABCs, and hopefully once we learn these, then we will be able to get to more advanced concepts in the next semester.